Okay, so this is Lecture 3, Part 2, a continuation of our discussion of derivatives. And to start off the lecture, I want to talk about the difference between delta y over delta x versus differential y over differential x. So let me write that down for you. So let's compare and contrast delta y over delta x versus differential y over differential x. There's a geometric difference between the two, and it's shown in this particular illustration, and we'll see this again and again. So let this curve be some hypothetical function. We don't know what it is, but we'll just call it f of x. So what I'm accentuating in blue is f of x. Okay, so here's f of x. And so points P and Q are points on the function f of x. Okay, and let's see what else here. Okay, so delta y over delta x would essentially be the change in the x values, okay, the distance between the abscissa of Q and the abscissa of P. Okay, so we call this delta x, and then delta y would be the change in the ordinates of Q and P. So this distance right here is delta y. All right? So you can kind of think of delta y over delta x as the slope of this secant line connecting P and Q on the function. Now, as far as differential y and differential x go, consider this tangential line to the function drawn at the point of tangent CP. Okay, and so differential x would be the same as delta x, so same distance. If we look at it in terms of geometric figures, differential x is the same as delta x. It's this distance right here. But the distinction is differential y. Okay, so differential y, the way that's figured is, okay, you drop a perpendicular from point Q to the x-axis, like so, and then you find this particular point, which is labeled T. So it got kind of masked out there. So there's point T, and then you find, and also you draw a horizontal to the x-axis through point P, and the horizontal intersects this perpendicular line to the x-axis at point R. All right, so the distance TR is differential y, and you can see that differential y is not the same as delta y. So essentially, and that's why we say that differential y over differential x is the slope of the tangent line. Okay, so there's the geometric difference between the two concepts. And you see how you construct differential y. You drop a perpendicular at Q to the x-axis, and then you draw a parallel at P to the x-axis. And where the perpendicular and the parallel intersect, we call it point R. And where the perpendicular intersects the tangential line, you call that point T, and so the difference TR is differential y. So if you have trouble calculating differential y, this would be the construction you could use to figure it out. And it's now also these two quantities, delta y over delta x versus differential y over differential x, they're all computed based on the point of tangency, where the tangent line is tangent to the function f of x. All right, so it all hinges on that point right there. Okay, so just keep those concepts in mind from a geometric perspective, and as we, because it's easy to lose these ideas when you get engrossed, say, in the calculations of some complicated derivatives, as we will do forthcoming. All right. So what next? All right. So let's see here. Let me pull up the page. All right. So now today In this lecture, we're going to talk about how to compute the derivative of a product of functions. Okay, so let's let f of x, and I'm using uppercase F, equal to a product of two functions. And the objective here is to calculate the derivative of big F of x. So we want big F of x, this right here. Now, I have an alternative proof. There's a proof outlined in section 3.2 of your text, but I've found that that proof is very confusing. I have a much simpler proof to offer up. And it's based on the definition of, using the definition of the derivative. All right, so the way we would proceed is like this. We say that f prime of x, the derivative of f of x, is the limit as h approaches 0 of the difference quotient for big F of x. Right? So we always resort to the fundamentals. So let's write that. Now, of course, there is the assumption that both f and g are differentiable on the domain of differentiability. In other words, we're not sticking an absolute value function in here and trying to calculate the derivative at, say, x equals 0. No, the assumption is that both f and g are differentiable. All right, so here's the definition of the derivative for f prime of x. Simple enough. So now what I'm going to do is I'm just going to plug in the product into the difference quotient. Okay, I'm going to basically use composition of functions, since we're all so good at that. So big F of x plus h is little f of x plus h times little g of x plus h. Okay, and then subtract off big F of x, which is, that looks, I got a stray mark there. G of x, all divided by h. And now we need to simplify this function. Okay, so the way I would propose to simplify it is I'm going to do a trick, an algebraic trick. All right, what I'm going to do, the objective basically is to transform the numerator into what amounts to a function that looks like the definition of a derivative. But in order to do that, I'm going to do a trick here. I'm going to add something to the numerator. I'm going to add, or rather not add, but subtract this quantity from the numerator, which I'll accentuate in red. And then if I subtract something from the numerator, I must add it back in to cancel its effects out so that we don't lose the original function. Okay, so I'll subtract and add this term, these two terms. Okay, and then we'll go back and plug in the rest of the original function. All right, so you can see I haven't changed anything. All I've done is subtract and add the same term to my difference quotient. So what this allows me to do then is it allows me to do some groupings and some algebraic groupings. Watch this. What if I were to factor out f of x plus h from the first two terms in the numerator? This is what I would get. I would get g times x plus h minus g of x. Okay, I'd get something that looks like this. And then if I were to factor out g of x from the last two terms in the numerator, I would get something like this. g of x times f of x plus h minus f of x, like this. Okay, so after factoring that out. All right, and then all of this, of course, divided by h. So what I'll do next is I'll split this big fraction into a sum of two fractions right here. I'll split it on this plus sign. I'll basically do what amounts to a partial fraction expansion. And so in doing so, I'll have limit as h approaches 0 of f of x plus h times g of x plus h minus g of x. Okay, now all of that divided by h, so I'm splitting. Okay, and then we'll have plus, okay, g of x times f of x plus h minus f of x divided by h. All right, so we have this. All right, and so now it's just a matter of playing with the limit laws. So I can distribute the limit operator term by term. So this would be the limit as h approaches 0 of f of x plus h times g of x plus h minus g of x divided by h plus the limit as h approaches 0 of g of x times f of x plus h minus f of x divided by h. All right, so now, again, apply the limit laws. So in the first limit, we have a product of two functions. So we can apply the limit law for a product of functions. And so we can say, what I'll do is I'll basically consider this as a function, and then f of x plus h is the other function. So distributing the limit operator to each factor in the product of functions, we'll have this times the limit as h approaches 0 of g of x plus h minus g of x over h plus the limit as h approaches 0 of g of x times the limit as h approaches 0 of f of x plus h minus f of x over h. All right. So this is the equivalent expression to the original expression, this. So we transform the expression into something we can now work with. All right, so now you should recognize that this expression is the definition of the derivative of g, right? So replace that limit with g prime of x. So we have the limit as h approaches 0 of f of x plus h times g prime of x. Okay, and you should recognize that this factor right here is the derivative of f. All right, so we can simplify that. So this would be the limit as h approaches 0 of g of x times f prime of x. All right. Now, so this term, consider this term right here, this factor. Well, note that we're taking the derivative with respect to h. No, I'm sorry, not the derivative, the limit. We're taking the limit with respect to h. And g of x is not a function of h. So for all intents and purposes, g of x is exposed as a constant to the limit as h approaches 0. So we can just simply drop the limit operator in the equation, because g of x is considered a constant as you take h to 0. All right, so that would be plus g of x times f prime of x. So the next thing we have to do is we have to simplify the last remaining limit operator right here. Okay, now at the start of this problem, okay, I mentioned that f and g both have to be differentiable on the interval for which we're taking this derivative. Okay, so recall from chapter 2 that if a function is differentiable, so recall, if a function is differentiable, then it is continuous. Now, why is that important here? Okay, all right, so we have f of x plus h is continuous. I should not say we have, we should say thus. F of x plus h is continuous. So what does that mean as far as the limit goes? Well, there is a limit law that I mentioned that says that if you take the limit as h approaches 0, or if you take the limit of the argument of a continuous function, which is what we're doing, we are taking the limit of the argument of a continuous function, then you can bring, okay, so if one takes the limit of a continuous function, then one can bring the limit operator inside the function and evaluate the limit of the argument of the function. And this only works if it's continuous. Okay, if it's not continuous on the interval of differentiability, then it will not work and you cannot do this. Okay, so as an aside, we have this. The limit as h approaches 0 of f of x plus h is equal to f, the function, times the limit as h approaches 0 of x plus h. And since this is simply a polynomial h, we can use direct substitution. And so after direct substitution, we make h equal to 0, so we have f of x. All right, so now we have a completed statement for the derivative of our product of functions. It is f of x times g prime of x plus g of x times f prime of x. right? So I'll restate it here. So the derivative with respect to x of a product of two differentiable functions, and if they're differentiable, they're continuous, but not vice versa, is equal to the first function, f, times the derivative of the second function, g, plus the derivative of the first function, f prime of x, times the second function, g of x. And I'll do some examples. So I would suggest memorizing this formula. It's a very important formula. Okay. All right, so let's do some examples. How about, next page, we do this. Consider, let's let h of x equal to the square root of x times e to the x. Right, and we want to calculate the derivative of h. Okay, so clearly h is a product of two functions. So usually what we do is we replace any radicals with their exponential forms. And so now we can use the product rule for differentiation. So that would be the first function, which is x to the 1/2, times the derivative of the second function, which from Lecture 3, Part 1, the derivative of e to the x is e to the x, plus the derivative of the first function, which is 1/2 x to the negative 1/2, times the second function. Okay, so let me show you how you can clean this up or simplify this. We can obviously factor out e to the x times x to the 1/2 plus 1/2 x to the negative 1/2. And let me show you how you can factor out the term in parentheses. Whenever you see a base, in this case the base is x, and it's and you have different exponents and you're trying to factor it, always factor on the exponent, the smallest exponent in the series. Okay, so this sum is called a series. So factor that term out. Always factor with the term with the smallest exponent. So the result then would be x to the negative 1/2 times e to the x. Okay, and then this would just be x, because x times x to the negative 1/2 is x to the 1/2. So this would be x plus 1/2. So this is the slope of any tangent line to h of x. Okay, so you just find an x value, identify your point of tangency, get the abscissa of your point of tangency, plug it in here, you'll have the slope of the tangent line at that point of tangency. And then you can get the equation of that tangent line at the point of tangency. All right, just to reemphasize the definitions. Okay, so we dealt with products. We know now how to take the derivative of a product of functions. So I guess the next extension would be to take the derivative of a quotient of functions. So let's do that. So let's let, again, let big F of x equal to the quotient of functions. So let me grab the note here. All right, so why don't we do this? Why don't we, so as before, we'll let f and g be differentiable functions. And so we want to, so we want to calculate the derivative with respect to x of this rational function, where f and g are both differentiable. All right, so this is what we're interested in knowing. Okay, so start off by saying big F of x is equal to the ratio of the two functions. Okay, and then we use, again, the definition of the limit of the difference quotient. The solution in the book is very difficult to follow, so I would suggest using my technique here. So f prime of x, big F prime of x, is equal to the limit as h approaches 0, okay, of f, oops, sorry, that's big F, that should be big F. Big F of x plus h minus big F of x over h, like so. And then we'll just wire in the definition for big F. So this would be the limit as h approaches 0 of f, little f of x plus h divided by little g of x plus h minus f of x over g of x okay, all over h. So now we have to process this. Okay, so if I go ahead and simplify the numerator, multiply upstairs and downstairs by the common denominator in the numerator, we get this. So the limit as h approaches 0 of f of x plus h times g of x minus f of x times g of x plus h all of that divided by h times the common denominator from the numerator. Okay, so you should understand how this happened algebraically. Okay, and so now we're going to use that trick we did with the product rule. We're going to add and subtract a quantity in the numerator. So we're left with the limit as h approaches 0 of f of x plus h times g of x, and the quantity this time I'm going to add and subtract will be, I'll subtract off first the product of the two functions, which will be f of x times g of x, and then on what I subtract I must add like this. Okay, so you see that that's 0, and then I'll finish off the numerator, which is minus f of x times g of x plus h. Okay, and all of that divided by h times g of x plus h times g of x. Okay, and so what does that offer up? Okay, so continuing on, what I'll do next is I'll take this h right here and I'll bring it up into the numerator. And so I'm going to do a couple of algebraic steps all at once here. So I'm going to have the limit as h approaches 0, and the first thing I'm going to do is I'm going to factor out g of x from these two terms right here. I'm going to factor out g of x from that. So I'm going to have g of x times f of x plus h minus f of x. Okay. And then I'm going to take this h and I'm going to bring it upstairs, like this. Okay, you can do that because h divides each term in the numerator, and you can do that. All right, and then so then I'll have this plus right here, so I'll have a plus, and then I'm going to factor out the f of x from these two terms right here, those two terms. So I'll have an f of x times a g of x minus g of x plus h. And then, of course, I can bring the h up, since h divides every term in the numerator. And then what I'll leave in the denominator of the bigger fraction will just be g of x plus h times g of x. All right, so now you can see the pattern emerging. I'll go ahead and use the limit laws. All right, so this would equal to the limit. I'll distribute the limit operator to each term in the numerator as well as in the denominator. So the limit as h approaches 0 of g of x times the limit as h approaches 0 of f of x plus h minus f of x over h plus the limit as h approaches 0 of f of x times the limit as h approaches 0 of g of x minus g of x plus h over h, okay, divided by the limit as h approaches 0 of g of x plus h times the limit as h approaches 0 of g of x. Okay, so now we just need to clean up the this expression. So we know this term evaluates to g of x. Okay, as per the previous discussion. And then this term is the definition of the derivative of f. Okay, and we have plus, and then this term is f of x. And then this term is the negative of g prime of x. Okay? And then we divide that by, okay, so as per the previous discussion, since g is differentiable, g is continuous, we can take the limit operator inside, use direct substitution, and so this is nothing more than g of x, and then of course this limit right here is g of x as well. All right, so now we can simplify this. Right in, okay, so this would be g of x times f prime of x minus f of x times g prime of x, and the denominator becomes g squared of x. So this is the rule for the derivative of a quotient of functions. All right, so and I'll summarize here. So the derivative with respect to x of the quotient of two functions is equal to the bottom function, g, times the derivative of the top function, f prime of x it is, minus the top function times the derivative of the bottom function, all of that divided by the bottom squared. Okay, and I would suggest memorizing this formula as well. When you work through the WebAssign, you'll encounter a lot of problems which ask you to compute the derivative of a quotient of functions. All right, so I guess we should work an example. Let me see if I can find a decent example. Okay, so let's do that on the next page. So for instance, let's let f of x equal to, say, x divided by x plus c over x. So we want to calculate f prime of x. Okay. So f prime of x, we can use the quotient rule for differentiation, would equal to the bottom function times the derivative of the top function, which is 1, minus the top function times the derivative with respect to x of the bottom function. Okay, and I'll just leave it like that for now because that's going to require some work. And then all of that divided by the bottom function squared. Okay, so now what is the derivative? We have that one derivative that we have to calculate. So as an aside, we need to calculate this derivative. Okay, and since it's a sum of functions, we go term by term, take the derivative of each term in the sum, and so this would be 1. C is presumed to be a constant, and then we can use the power rule for x to the minus 1. So that would be, as you can recall, that the derivative of 1 over x is negative x to the minus 2, which is equal to 1 minus c over x squared. All right, so we'll just substitute this result in there. Okay, so f prime of x is equal to x plus c over x minus x times 1 minus c over x squared divided by x plus c over x quantity squared. And we can simplify the numerator. So that's equal to, well, the x's cancel. That would equal to 2c over x times x plus c over x squared. Okay, and so that is equal to 2c divided by x times x plus c over x squared. Okay, all right. What else can we do? Okay, I want to show you another example of the utility of using the product rule for differentiation. Suppose I gave you something that looked like this, and I asked you to calculate its derivative. y plus. Now, clearly, we have a product of two binomials. And you really don't want to have to get into the game of having to multiply these two binomials together to get an expansion of y. Just use the product rule for differentiation when calculating the derivative of this expression. So it would be the first factor, which is this, times the derivative with respect to y. Oh, I'm sorry, it's a function of y, not x. I beg your pardon. So let me make that adjustment. This should be y. Okay, you have to be careful. F prime of x would be 0 for this case because it's not a function of x. It's a constant, right? So let me rewrite that. So f, you have to pay attention to the variable that you're differentiating with respect to. Okay, so it would be the first factor times the derivative with respect to y of the second factor plus the derivative of the first factor, the derivative with respect to y of the first factor, times the second factor. Okay, so this would be the product rule for differentiation. So notice we didn't have to multiply the two binomials out. Now all we do is we just simplify the derivatives. So this would be y to the 1/2 minus y to the 3/4 times, okay, so distribute the derivative operator, so that would be 1 plus 15y squared plus, okay, distribute the derivative operator in the binomial, that would be 1/2 y to the negative 1/2 minus 3/4 times y to the negative 1/4 times y plus 5y cubed. Okay, so, and you can leave it like that, leave your answer like that. So notice we didn't have to multiply any factors, just use the product rule. So that's what it bought us. Okay, so let's see, what next? What else do we want to calculate derivatives of? What other kinds of functions? That's what the topic of this section is. All right, so yeah, so I guess that would leave us with having to calculate the derivatives of trigonometric functions. All right, so let's give that a go. How about we calculate the derivative of the sine function? So that's our objective. And this would be, by the way, this would be section 3.3 of your text. Okay, so this would be section 3.3. All right, so to calculate the derivative of the sine function, we use the fundamental definition, the limit of the difference quotient. All right, so this would be sine times x plus h minus sine of x divided by h. All right, so now the problem is we have to know what the sine of x plus h is. So if you have recent experience with trigonometry, you know you could use the formula for the sine of a sum. Okay, so it turns out, and if you don't know this, you can go to my trigonometry website, and I have these expansion formulas in the literature on my trigonometry class website. But the identity, I'll give it to you here, that we'll use for the sine of a sum is equal to sine x cosine h plus cosine x sine h. Okay, so we'll use this trigonometric identity for the limit calculation. So plugging that in to the difference quotient. We have the limit as h approaches 0 of sine x cosine h plus cosine x times sine h minus sine x all over h. Okay, so we can split this expression into two partial fractions. Well, before I do that, let me see if I can do a factoring. No, well, what I'll do is I'll group these two terms together right here, and then I'll do a partial fraction expansion. So we'll get this. The limit as h approaches 0. I'm going to combine a couple of algebraic steps into one here. So we'll have sine x cosine h minus, see, I'll associate these two terms. Okay, and then the partial cosine x sine h over h, like this. Okay, so we have this. And then I'll just use the limit laws. Okay, so we know cosine and sine are both continuous on their domains, so we can easily use the limit laws because the limits exist everywhere. So distributing the limit operator to each term in the partial fraction expansion, of course what I'll do is I'll factor out sine x. I'll factor out this sine x right here. And so that would be cosine h minus 1 over h. I can do that. Okay. Plus the limit as h approaches 0 of cosine x times sine h over h. All right, so we can do that. All right, so now we can just use the limit laws for the limits of products. All right, so this would equal to the limit as h approaches 0 of sine x times the limit as h approaches 0 of cosine h minus 1 over h plus the limit as h approaches 0 of cosine x times the limit as h approaches 0 of sine h over h. Okay, so we know that this term right here, that's just sine x, because sine x is a constant with respect to the limit operator. Okay, and so times the limit as h approaches 0 of cosine h minus 1 over h. And we know that this limit is cosine x. And this limit right here, we proved through a geometric construction. So that's equal to 1. Okay. All right. So the only thing that remains to be done is to clean up this limit right here. Now, if we were to use direct substitution, we know that the cosine of 0 is 1. So we would have a 0 over 0 case. So this limit is an indeterminate limit. And you know the rule, indeterminate limits evaluate to a number for the most part. So we have to work on analyze what that limit is. All right, so that's a little piece that needs cleaning up for this derivation. So the limit as h approaches 0 of cosine h minus 1 over h. All right, so what I'm going to do is I'm going to rationalize the numerator. I'm going to multiply upstairs and downstairs by the conjugate of the numerator. See that? And so that becomes the limit as h approaches 0 of cosine squared h. So we have a difference of, this evaluates to a difference of 2 squares, right? Cosine squared h minus 1 over h times cosine h plus 1. Like that. Okay. But we know that cosine squared h is 1 minus sine squared h, okay, by a trigonometric identity. And so if we plug that in, we'll have the limit as h approaches 0 of negative sine squared h over h times cosine h plus 1. Still an indeterminate form when we plug in 0. All right, so let's factor the numerator. We can do that. So this would be the limit as h approaches 0 of negative sine h over h times sine h over cosine h plus 1. Okay, and so distribute the limit operator term by term in the factor, in the product that is, term by term in the product of those two functions. Okay, sine h over cosine h plus 1, and then we know that this limit is 1, and this limit, well, 0 is in the domain of this rational function because the cosine of 0 is 1. 1 plus 1 is 2, so the denominator would equal to 2 after direct substitution. The numerator would be 0 because the sine of 0 is 0, so this limit is equal to 0. All right, so that we plug that 0 back into the original expression, so which is here. So this is equal to 0. All right, so now we have a formula for the, okay, and so, well, since this is equal to 0, then all of this is equal to 0, and so we're only left with this as being the derivative of the sine function, which is cosine x. So the derivative with respect to x of sine x is equal to cosine x. And I expect you to memorize this. Okay? All right. Now, we can do the same, a very similar approach for the derivative of the cosine function. And I'm going to leave that to you as an exercise. So, but I'll write the formula, and I'll have an expectation that you'll be able to prove this. Okay? The derivative of the cosine function is equal to minus the sine function. Okay? So I'm going to expect you to prove this, but I'm going to use this result in deriving the derivatives of the other trigonometric functions, which comes next. So let's see here. All right. So we can now prove the derivative, what the derivative, or derive what the derivative of the tangent function is. So let's do that next on the next page. All right, come on, computer, cooperate. Jeez. Okay. So we want to calculate the derivative with respect to x of the tangent of x. All right, so in this case, we replace the tangent function with its definition, its rational function definition. And we know that the tangent function from trigonometry is sine of x divided by cosine of x. Right? And so instead of using the limit of a quotient, the limit of the difference quotient, we can use the quotient rule for differentiation. Okay? And so applying the quotient rule for differentiation, it would be the bottom function times the derivative of the top function, and the derivative of the top function is cosine x, minus the top function times the derivative of the bottom function, which we said was minus sine x, and which is what you're going to prove, all divided by the bottom function squared. Okay, and so after simplifying, the numerator becomes 1. Okay, and by definition, 1 over cosine x is secant x. So this is secant squared x. Okay, so that's what I expect you to memorize as well. And so knowing this, okay, you can now calculate the derivative with respect to x of the cotangent function by using the definition of the cotangent function. And I will leave that to you as an exercise. Okay, so you'll obviously have to use the quotient rule for this rational function, cosine x over sine x. And in doing so, the result you'll get will be minus cosecant squared x. Okay? Okay, so I expect you to be able to prove that. Likewise, we can calculate the derivative. How about the derivative with respect to x of the cosecant function? I'll do cosecant, and I'll expect you to be able to do the derivative of the secant function. Okay, so that would be replace the cosecant function by its definition of in terms of the rational function, so that would be 1 over sine x. Okay, and then we just use the quotient rule for differentiation. So that would be sine x times the derivative of the top, which is 0, minus 1 times the derivative of sine x, which is cosine x, all over the bottom function squared. Okay, and so that would just be minus cosine x over sine squared x. Okay, and so that would equal to the negative cotangent of x times the cosecant of x. Okay, so memorize that as well. And so I'll give you okay, so I'll expect you to validate that the derivative with respect to x of the secant function is equal to tangent x times secant x. Okay, so I have an expectation that you can prove that. All right. Okay, so let's do, trying to think here, what are some interesting examples? Okay, okay, so I've got a couple of examples we can. So how about we solve this kind of problem? The limit as x approaches 0 of sine of 7x divided by 4x. Okay, well, we know that the limit as theta approaches 0 of sine theta over theta is equal to 1. Okay, so we use this fact to solve this particular limit problem. So if we were to what's called augment the denominator, like so, what if we were to multiply the denominator by 7/4? Like that. Now if we multiply the denominator by 7/4, we have to multiply upstairs by 7/4 as well. Okay, so we can do that. And now the 7/4, this particular 7/4 can become a constant to the limit problem. Okay, so we can kick that out. And so we're left with the limit as x approaches 0 of sine 7x over 7x. And of course, this limit is just 1. So the answer to this problem would be 7/4. Okay, so I think there are going to be some WebAssign questions like that. All right, what else can we solve? Oh, okay. How about the limit as x approaches 0 of x times the cotangent of x. Where did my page go? Oops, I must hit the space bar. Sorry. Okay, now the question is, can you use direct substitution here? Well, you can't, because the limit operators stipulate that in order to use direct substitution, okay, in other words, you can't do this for the cotangent function, because the limit as x approaches 0 of cotangent function actually is equal to infinity, right? Because that cotangent is cosine over sine, and then you send the denominator equal to 0 and you shoot off toward infinity. Okay, so actually, okay. Yeah, so x equals 0 is actually a vertical asymptote for the cotangent function. So really, this limit doesn't exist. Okay, sorry about that. So this limit doesn't exist. So you can't use the limit operators for this product. Okay, so what you'll have to do is and so effectively, after direct substitution, this is not quite an indeterminate. Well, it is an indeterminate form, because you have essentially a 0 times infinity or a 0 times negative infinity, which is an indeterminate situation. So replace the cotangent function with its definition in sine and cosine, and then you'll readily see the result. So this is the limit as x approaches 0 of x times the cosine of x over sine x. Okay, and so this is equal to the limit as x. Now I'll factor this function into a product of two functions. And so now we can see that if we consider this is a product of two functions, we can distribute the limit operator to each factor in the product, because the limits of each of the factors do exist. Okay, so we can do that, just knowing the definition of the cotangent function. And we can use direct substitution on the second factor, okay, because 0 is in the domain of the cosine function, so that's just 1. And this you should recognize as being, Well, you can apply the limit operators, but that's still 1. That's of the same form as this right here. It's the same form. Okay, you just take the reciprocal of the function and then apply the limit operator. So I'll leave it to you to verify that that is the case. So this limit is 1. So the limit as x approaches 0 of x times cotangent x is 1. All right, so be forewarned. What can we do next here? Take some more derivatives. Okay. All right, yeah, so next page is some more interesting calculations. So how about we take the derivative with respect to x of this function? How about y is equal to 1 plus sine x divided by x plus cosine x? So in this case, we'll have to use the quotient rule for differentiation. So that would be the bottom function times the derivative with respect to x of the top function, which is simply cosine x. Okay, notice how I'm able to skip steps because I have knowledge of how to take the derivative of a sum of functions, minus the top function times the derivative of the bottom function, which is 1 minus sine x. All divided by the bottom function squared, which is x plus cosine x squared. Okay, and we can maybe attempt to clean this up a bit. So we'll have x cosine x. Oh, by the way, this is y prime. Okay. Okay, make that clear. Okay, so y prime is equal to x cosine x plus cosine squared x minus, okay, and this would be 1 minus sine squared x. Okay, and we know that 1 minus sine squared x is equal to cosine squared x. Okay, all divided by x plus cosine x squared. And simplifying, that becomes, well, let's see, it looks like the cosine squareds will cancel. So we're left with x cosine x divided by x plus cosine x squared. Okay, and leave the answer like that. All right, let's calculate another one. So how about we calculate the derivative of this function? Y is equal to 1 minus secant x divided by tangent of x. So we want the derivative. So again, we'll use the quotient rule for differentiation. So y prime is equal to the bottom function times the derivative of the top function. And I told you to calculate the derivative of the secant function, and that's just the derivative of the secant function is secant x tangent x, okay, and we have the subtraction here, so we have to put the minus sign out in front. So the bottom function times the derivative of the top function, which is this, minus the top function, which is 1 minus secant x, times the derivative of the bottom function, which we know to be secant squared x. And then all of that divided by the bottom function squared, which is tan squared x. Okay, and we can probably try and simplify that. So y prime is equal to minus secant x tangent squared x minus secant squared x plus secant cubed x. All of that divided by tangent squared x. And I suspect that could be simplified in some fashion. Secant x times 1 minus secant x. Yeah. So let's see if we can go further with this simplification, perhaps using some trigonometric identities. So let's see, if we were to factor out a secant x in the numerator, we would have secant x times a negative tangent squared x. Let's see, is that the one? How about we don't, I don't like, try a different way. Let's see, leave the first term alone. Minus secant x times tangent squared x. We'll factor out a secant x from the last two terms in the numerator. So we'll have, let's factor it out this way. Secant x times a negative, let's see here. I'm tempted to think that that's as far as we can go with this, assuming I did it correctly. I don't see, I'm trying to look for a pattern using the fact that 1 plus, let's see, secant squared x is equal to, let's see, 1 over cosine squared. I think that's 1 minus secant squared x. 1 minus secant squared x is equal to tangent squared x. Is that right? Let's see, this would be 1 over cosine squared. One minus 1 over cosine squared. Okay, so this would be cosine squared, sine squared. Yeah, I think this is the identity, like this. So that would be cosine squared. Yeah. So I don't think we'll be able to use this trig identity to simplify this function any further. I'm not seeing it. Secant squared times 1 plus secant x. No. So that, I think that's as far as we can go with this. Yeah. So we'll leave it. We can leave it like that. That's fine. Assuming I did it correctly. There is I think on the class website there is a derivative calculator that you can use to check this. So you can go to try and check your answer using that. All right, let's do another example. How about we calculate the derivative of this function? Y is equal to let's see, that is cosecant theta times theta plus cotangent theta. It's theta plus, and so we can use the product rule for differentiation. So y prime is equal to cosecant theta times the derivative of the second term, which is 1 minus, okay, so we know the derivative of the cotangent function, which I asked you to prove. That would be 1 minus cosecant squared theta plus, okay, now the derivative of the cosecant function is minus cosecant theta cotangent theta times theta plus cotangent theta. Okay. And let's see, can we simplify this? I don't think so. Yeah, so we can leave the answer like that. All right, and let's do a limit problem. How about the limit as x approaches 1 of sine of x minus 1 divided by x squared plus x minus 2. Okay, well, I really don't, if we use direct substitution, of course, we'll have an indeterminate form. So I really don't want to have to expand the sign of a difference of terms. But what we can do is we can factor the denominator and get some hints into the solution of this problem. So if we factor the denominator, we'll have what, x plus 2 times x minus 1. And then we can, okay, and so this becomes, well, okay, so what we will have to do is we'll have to replace x minus 1 with a variable. So how about, let me show you, this is called a change of limit index technique. All right, so let's let y equal to x minus 1. Okay, if x approaches 1, then since x minus 1 is a polynomial, we can use direct substitution. Y approaches 0. Okay, so using this fact, why don't we change the problem as a limit as x approaches 1 to a limit, an equivalent problem in y. Okay, and the reason why is so that we can replace the polynomial argument in the sign function with a single variable. So now the problem becomes this. And so x is y plus 1, right? So we replace x with y plus 1 plus 2. Okay, so this x, solve for x in this equation, and you'll see that x is equal to y plus 1. And then I just plug that value of x in right there. Okay, and so now you can readily see that this is simply 1 times, I won't go through the explicit details of the limit laws, but this would be 1 over 1 times 1/3 after direct substitution. And of course, you know what this limit is. That's 1. And you can use direct substitution for this factor, and that's 1/3. So the answer to this problem would be 1/3. Okay, let's see if there are any more problems we can work in this section. Yeah, I think there are a couple more. Yeah, so let's take the derivative of this function. F of x is equal to secant x divided by 1 plus tangent x. And so what is the derivative here? So f prime of x is equal to the bottom function times the derivative of the top function, So that would be secant x tan x minus the top function times the derivative of the bottom function, which is simply secant squared x, divided by the bottom function squared. Okay, so we can just leave the answer like that. I see no reason to simplify it. Secant x, yeah, secant cubed. I think there might be a trig identity in play here, but I'll leave it to you to figure that out. But for all intents and purposes, we'll leave it like that. We won't mess around too much with the trig identities, having to figure out what that is. Okay. All right, so some more problems. Okay, checking here. All right, so how about we consider this function? So if I give you y is equal to cosine x over 2 plus sine x, the question is, where is the tangent horizontal? Now, what is it about horizontal lines? Do you know the slopes of a horizontal line? We know that the slope of a horizontal line is equal to 0. So what is the slope of the tangent line to this function? Well, the slope of the tangent line to this function is the derivative. All right, so y prime, which is equal to the slope of the tangent line. Okay, we have to use the quotient rule for differentiation for this function. Okay, bottom times the derivative of the top minus the top times the derivative of the bottom right, divided by the bottom squared. Now the bottom function is never equal to 0. And why is that? Because the sine function is never less than -1. And so no matter what x you put in, the denominator is never 0. So to set this equal to 0, all we have to do is let the numerator equal to 0. So we have to simplify the numerator now. We're forced to simplify. So we have the requirement that -2 sine x minus sine squared x minus cosine squared x is equal to 0. And so now we have to solve a trigonometric equation from trigonometry. So now we have -2 sine x. Okay, well these two terms equal to -1. Okay, and so I'll bring the -1 over. And so we have this, and so now we have sine x is equal to -1/2. Okay, and so you can go to my trig website and find out which points the sign of a number is equal to -1/2, and that turns out to be at the sine of 60 degrees and the sine of I'm sorry, not 60 degrees, the sine of what, 300 degrees, and the sine of 240 degrees. So this would happen at x equals to 7 pi over 6 radians, or at 11 pi over 6 radians on the unit circle. All right, and now we just extend this by periodicity. Okay, and so at x equals to 7 pi over 6, the output is what of the function? So if we plug in 7 pi over 6, so let's do that. Y is equal to, and if you don't know the 7 pi over 6, get with me and I'll show you where I got the 7 pi over 6 and 11 pi over 6. On my trigonometry website, there's a diagram which shows you how to get to the how to figure out what values of x makes sine x equal to -1/2, and I can show you how to use that if you're not familiar or if you've forgotten. But anyway, to move things along, and of course that chart that's on the trig website you can use for your tests if you encounter a problem like this, and you can ask in class or get with me for an understanding of this. So let's evaluate the function at 7 pi over 6. Okay, well, the cosine of 7 pi over 6 is, let's see, that would be, we said this was 240 degrees, so that the reference angle is pi over 6. So the cosine of pi over 6 is the square root of 3 over 2, so this would be negative square root of 3 over 2 divided by 4 halves divided by 3 halves. So this would be the negative of the square root of 3 over 3. Okay? And let's see, if we were to evaluate at x equals to 11 pi over 6, this would equal to, well, the cosine of 11 pi over 6 is the square root of 3 over 2 divided by 3 halves, and so that's equal to the square root of 3 over 3. Now, okay, so we also have the notion that the function is periodic, okay? So sine x equals to -1/2 at periodic values of 7 pi over 6. And the period of the sine function, as we know, is 2 pi. So for every 2n pi, n being an integer, okay, these would be the values of x where sine x is equal to -1/2. Also at periodic values of 11 pi over 6, okay, by periodicity. So we have an infinite number of abscisses where the sine x is equal to -1/2. So the answer to this question is, where the tangent lines are horizontal, you would write like this. You could say 7 pi over 6 plus 2n pi. This would be the abscissus on the curve, and then the corresponding ordinates would be negative square root of 3 over 3. So that's the locus of a set of points, and then the other places would be 11 pi over 6 plus 2 pi n, and then the square root of 3 over 3. And some of these are probably, I'm willing to say that these are what, local minimum points, and these would probably be local maximal points. Okay, so an interesting problem. All right, so let's do some more, a couple more for this section. Maybe I can just copy and paste them. Let's try doing, say, problems, a couple of problems here. I'll just paste them into whiteboard here. 1 second while I copy them into the whiteboard session. So I think this will be problem 55 of section 3.3. I'm not sure. You can check, but nevertheless, we'll do it anyway, irrespective of where it is, right? So in this case, look at this figure. We have a circle, okay, and S, okay, S is the arc subtended by angle theta, okay? So here we have arc S. I'll accentuate in blue. Okay, and it's subtended by this angle theta. Okay, this is so theta. You can see that the initial side and terminal side of angle theta defines the arc S on the circle of radius r. So r is the radius. And d, what is d? Well, d is the chord of the arc defined by S. So d is the chord of the angle subtended by theta. And so here's the problem. We want to find the ratio of the arc length divided by chord length as theta approaches 0 from angles bigger than 0. So in other words, what happens to that ratio as we make the initial side right here of the angle go toward the terminal side? What happens to that ratio? All right, so let's do the calculation. It's an interesting calculation. So we have, by definition, arc length is equal to the radius of the circle times the measure of the subtending angle in radians. Okay? And we also know that the sine of theta over 2, okay, so the sine of theta over 2. So what would happen if we divided theta over 2? Well, let's figure that out. Here I have the answer, but how do we know that's true? So let's prove that. Let's do a little trigonometric proof here. All right, so now if I were to draw a bisector for angle theta, okay, so here, this black dashed line, which I'm accentuating in yellow, that's a bisector. So this angle is theta over 2. And so clearly, this is a right angle. That's a right angle. So the sine of theta over 2 is the opposite, okay, the length of the opposite side, which now this bisector, not only does it bisect angle theta, but it also bisects the chord D. And that's a concept carried over from geometry. So the bisector makes the opposite side length of D over 2, and then we have the radius. So sine theta over 2 is D over 2 over R. So why did I choose to calculate that? Well, okay, because the reason being is that we can get a formula for D. Okay, that's the only way we can grab a formula for D in terms of R. Okay, because R stays fixed for this circle. And we need an expression for D, okay, in terms of R. So now we have an expression for D in terms of R, all right? So that's why I took 1/2 the angle. I used my knowledge of trigonometry as well as geometry. Well, not so much trigonometry. Well, yeah, trigonometry, because I had to take the sine of an angle over 2, but this is more of a geometry problem. Whenever you have a subtending angle and you bisect the subtending angle, you also bisect the chord for the subtending angle. Okay, and doing that, we now have D as a function of theta. And we also have S as a function of theta. So can you see why now we have to recast or reformulate S and D in terms of theta, so that we can take the limit, because we're taking the limit as theta approaches 0. We replace S of theta with a function of theta divided by D of theta. So we have to use what are essentially considered parametric equations. So S and D are functions of theta. All right, so now we just make the substitution. So here's the limit problem. Replace S with its definition in theta, and then replace D with its definition in theta. Okay, and do we have any information about R? Well, let's see. Oh, the R's will cancel, right? And then the 1/2, okay, the 1/2 can come upstairs like this. So take this 1/2, move it upstairs, and we have the limit as theta approaches 0 plus of theta over 2 times divided by sine theta over 2. And of course, that is the limit that we're all familiar with, okay, and that's equal to 1. So, interesting problem. I guess the trick is what you guys would probably have issues with both would be these two formulae, especially trying to get d as a function of theta. And that's the only way. All right, so kind of like you to be aware of these kinds of techniques for looking at a geometric figure and defining variables in terms of properties of the geometric figure. This is going to loom large toward the end of this chapter 3 and as well as chapter 4. So kind of get in the habit of resurrecting your knowledge of geometry and trigonometry to develop equations or formulate equations which model or describe certain variables in the figures. Okay. So if you have any questions about this particular problem, which is kind of important, come see me or send me an email. All right, so let's do number 54, problem number 54 of the text. So let me copy that one. I believe this would be in, I think this would be 54. It may not be, maybe numbered differently. But I'll call it problem 54, and it's in the text somewhere. Okay, so here's the problem right here. We want to find this limit, and A theta is the area of the semicircle. Okay, so we have this semicircle right here. Okay, and what is B theta? B theta is the area of the triangle. So we have the triangle, and we want to find the limit as this theta. So theta is, what is theta? So this is theta right here. Okay. So what happens as theta goes to 0? What is the ratio of the two areas? Okay. So again, so what do we have here? So the area of triangle, or the semicircle, the area of the semicircle is so it starts out like this. What's the area of a semicircle? It's pi halves r squared, right? And it looks like r is labeled as 10. Is that right? No, actually the radius would be, we don't know what the radius is. We know this length is 10, this length is 10. Do we have any information about what r is? Not yet. Okay. Okay, so r we'll consider to be the radius of the semicircle, like that. Okay, and then b theta, what's the area of the triangle? So that would be 1/2 the base times the height, right? So that would be 1/2. The base length is 2r, and the height. So we want to find this limit. So obviously what we have to do is we have to replace both r and h in terms of theta. Okay. All right. So now again, we have it's just like the same problem as before. The angle theta subtends arc PQ. Okay. So theta subtends the arc PQ. Okay, and so if we were to draw a bisector for angle theta, like so, okay, so a bisector for angle theta, so we have now this angle being theta over 2, and we have r on, and we basically split the diameter of the semicircle into 2r like this. Okay, so we have this relationship. We have the sine of theta over 2 is equal to the length of the opposite side r divided by the length of the hypotenuse, which we're taking as 10. And so now we can solve for r in terms of theta. So we have an expression for r in terms of theta. And so now we need to replace h with its expression in terms of theta. And so we know that h is the height of the rectangle. So what is h? H is this green length right here. So we know that the cosine of theta over 2 is adjacent over the hypotenuse length, so now we have an expression for h in terms of theta. Okay, and so all we do is wire it up. So here's our limit question, okay, right here. That comes from this expression and the pi halves, okay. So in a limit problem, the constants go out. So here we kick the constant out. The limit as theta approaches 0. Well, we can do a little cancellation, so that would be r over h. And so r over h is what? What is r over h? Well, just look here. Look here. You can do it by inspection. R over h, the tens cancel, so that would just be the tangent of theta over 2. So pi halves times the limit of theta approaches 0, tangent theta over 2. Well, 0 is in the domain of the tangent function, so you can use direct substitution. We know that the tangent of 0 is 0, so the limit is 0. Okay, another very interesting problem. So again, what I want you to understand is that you formulate the limit problem in terms of the variables. Okay, you parameterize the problem, identify the heights and radii and whatnot, and then replace these variables r and h with their expressions in theta. Okay, so that's the technique, a facility that you need to work on. We'll be doing a lot of that. Okay, and let's see here. Okay, one last problem. Let's see. For this section, I think, well, or one more problem. I think this may be the last problem of the section 3.3. I'll check in just a second, but let's do this problem. I'll talk about it, and we'll see this later, more kinds of these kinds of problems later on in this chapter. But in this case, suppose we have a ladder leaning against the wall, like so. Okay, and it makes an angle theta with the wall, and the ladder is 10 feet long. And so what we want to know is, okay, so the ladder starts all of a sudden sliding down toward the ground in this direction. And then the foot of the ladder, of course, will slide this way in this direction. So we want to know the change of the position of the foot of the ladder with respect to theta. So as the ladder slides down, theta changes, okay? Eventually theta will go to 0, right? So what is the change in position of the foot of the ladder with respect to the change of the theta? Well, we know that sine theta, okay, well, we know that the foot of the ladder starts out at x feet from the wall, okay? So at any particular point in time, the sine of theta is equal to the opposite over the length of the ladder. And the length of the ladder, of course, is fixed. So all we do is we take the derivative of x with respect to theta, and we know that the derivative of the sine function with respect to theta is cosine theta, and so dx over d theta is 10 cosine theta. Okay, because x is equal to 10 sine theta. So that was pretty easy, almost trivial. Are there any other things that we need to deal with in this section? Okay, we've done that. Okay, so I believe that would conclude section 3.3 and this lecture sequence. So in the next lecture, we'll talk about how to compute the derivative of a composition of functions. All right, so that will be it for this particular sequence. I will stop recording now.